Well, hello and welcome back to Engineering 201 Electrical Fundamentals, and we're working on experiment number 3 this week. So let's head to there, change views on you here, and see what we can do. So again, this is maybe a little bit hard to see, but you've got this in hard copy or should have it in front of you. Experiment number 3, we're going to be working on a circuit that looks like this, and you're going to get to practice our mesh analysis on this, and also again comparing our measurements to our calculated values and so forth. So this is the circuit. We've got several resistors around here. We've got one source there like that. And I think those values are listed there. We'll check our circuit. Our circuit is right here. And again, I've tried to make the circuit look fairly similar to the drawing, and we'll get to that in a little bit. One of the things that we're going to be asked to do is in the pre-lab here, you can see that we need to calculate the values for currents I1, I2, and I3. And this is just important as you go into a lab to have some idea of what is this current. I1, that's this current in here. This current I2, that's that current in there. And finally, the current in here, that's I3. Have some idea of what those currents are. So I'd recommend that you stop this video, that you sit down, and that you figure out what those are. So to help you do that, I've laid out some of the equations here. You've got, you could do it with node analysis, but mesh is probably going to be a lot easier on this problem, good practice on this problem. And in the past, this is where some students in lab really sat down and figured out, oh, I need to learn how to do mesh analysis. So like I said, spend the time, pause this, and get this figured out. Figure out what I1 turns out to be, what I2 turns out to be, what I3 turns out to be with these values. You'll get to do it again with the actual values, because the actual resistor values will be slightly different. You can do it again with those, but for now, just use these values. So to help you with this, I decided to write the equation. So you're going to have one equation here, and you're going to have a second equation there, and then I'm not going to spoil the surprise. You'll have a third equation there. 3 equations that will allow you to solve for 3 unknowns, I1, I2, and I3. So let's look at this first equation. How did I write this? Well, I started here at this point, and as you go around here, you have a drop, and I've taken drops as positive. This drop is given by Ohm's law. Remember, V is equal to IR. So the product of current times resistance is your voltage, and this is a drop. So I have I1 times R1. And then as I go and move around here, I am now looking at the current going through that, and that's a drop. That's going to be I1, because that's going with us. That's going to the left. And minus I3, because if you look at I3, that's opposing us. So this is the direction of I1. This is the direction of I3. I guess that's showing up okay. So that's why I have I1 minus I3. And then when I go over here, likewise, you're going to have I1 minus I2, because I2 is opposing you. That gets you back to your starting point. Kirchhoff says that's equal to 0. So then the next one I decided to do is this one around here. So if I start at this point here, and I move up through this source, that's a gain. I go from negative to positive. It's a gain. So I take that as a negative, a drop. I'm going to take voltage drops as positive, so if I have a voltage gain, that would be a negative sign. And if you don't like that, you can use the other convention. You just have to be consistent. That would be the same as multiplying this equation through by minus 1. You'd have the same equation. So minus Vs, then I get up here, and now I have R2 times I3. That's now going in the direction we're going. I3 is going to the right. I1 is opposing it, so it's minus I1. So R2 times I3 minus I1. And then as you turn and you go down through here, you're going to have I3 times R3 and also I3 times R4. So make sure that you can write those equations. make sure and come up with the equation going around here. The one thing I will tell you, if you go around this thing clockwise, you're going to go from positive to negative. So that's going to be a drop. So this source would be a positive Vs in that equation. So be careful of that. It won't be a negative like in that one. When you get done with this and spend the time to make sure that you can sit down with a blank piece of paper and write this out, when you get done, you're going to have 3 equations. You can solve that, probably put it into a matrix form. And whether you do that matrix by hand or with your calculator, row-reduced echelon form is a pretty popular method for folks. You're going to solve then for I1, I2, and I3. So we'll leave that like that. Then we're going to be asked to connect the above circuit, double check it, measure I1, I2, and I3. Well, remember when we're measuring currents, like we learned last time in the last lab, when you measure the currents, for instance, if I want to measure I1, I have to disconnect the circuit. The circuit was normally going through there. I'm going to have to physically open the circuit, and I'm going to put my ammeter in there. It doesn't matter whether I'm using a digital ammeter or an analog ammeter. If I want to measure the current, I have to look at the current going through that meter. So I'll have to open this up and put the meter in there for I1, open this up and put the meter in there for I3, open this up and put the meter in there for I2. So that's how we'll measure those currents. And then measure node voltages A, B, C, and D with reference to ground. Okay, so I'll put one lead of the meter. Got a meter right here, should be able to do that. So I'll take the black lead here, put that at ground, and take the red lead. That's going to be the voltage at A. There's the voltage at B. There's the voltage at C, and so forth. Then measure the voltage AC, CD, and DA, and so forth. For instance, AC is going to put the positive red lead on A and the black on C. So if I put the, like I said, the red on A, the black on C, that's going to be voltage AC. If I want voltage CD, then there is CD like that. Okay, so that'll be pretty straightforward. And I think that's it for the measurements. Well, let's talk a little bit more about those voltages. So we're going to measure voltage C. So this is the voltage at C with respect to this ground. We're going to measure the voltage A, which is the voltage at A with respect to this ground. And we could rewrite these out for shorthand. I just say that this is VA, this is VC, and that's really the voltage at A with respect to ground, or the voltage at C with respect to ground, and we could be more descriptive in those if we wanted to. The voltage A being the voltage A with respect to ground, that's how you read that, and the voltage C being the voltage at C with respect to ground. So then if you look at this as a path, okay, there I get real fancy, and highlight this path. So I've got a path that looks something like that, right? Okay, that's a closed path. Kirchhoff's law says that the sum of the voltage drops and gains around there is equal to 0. So let's say that I start right here and I go up this way. I've gained VA, so that's my VA term. And then as I go from there to there, I am dropping because I'm going opposite the arrow. Here I was going with the arrow, so it's a positive. Here I'm going opposite the arrow, so it is a negative. So there's positive VA, then from there to there is minus VAC, right there, minus VAC. So VA, positive VA, and then minus VAC, and then how do I get back to here? Well, I have to go minus VC, because again, I'm going against the arrow. So minus VC, minus VC. So the only reason that this VA was positive is because that's the only one I was going with the arrow. Kirchhoff said, because I get back to that point, it's equal to 0, and if I solve for that, I have that VAC is equal to VA minus VC, and I think that'll come up eventually. So Think of that in terms of Kirchhoff's voltage law. Well, let's see. The questions then, maybe we'll save those for the end. Put those up there and hopefully address those before we disband. So let's get on with the lab here. I think you can see it. It's slightly off screen here where I've got the sources, but I've got the positive source coming into this bus. So all of these holes that are going down here, so these two resistors are in the positive. So that's going to be this connection right there. You see right there. And then this one is, I've essentially set up this bus that is a negative. So that's that connection right there. So between there and there is the positive and negative. And you can see I've again endeavored to make these look similar to it on paper. This resistor being there, these two, and those two, and then finally the R4s down there. Okay. Now, before I get too far, I probably need to record the actual value of these resistors. And to do that, I should turn this off. And remember, if I just take and measure the resistance, so if I put my meter up here, put it on ohms, I have the power off so I can measure resistance safely. Turn the light on. I think that makes it a little easier for you to see. If I try and measure the resistance of, for instance, this one, I've got 97 ohms. And it's actually fairly close, but I don't think we're getting the right answer because I am getting the equivalent resistance. Okay, let me try this one up here. That's 432, but what should it be? It should be about 1K, so that's way off, okay? So if I'm measuring this that I'm hoping is 1K, it's nowhere close to 1K. And the reason is because, again, I'm getting the equivalent resistance of this whole thing, so I need to pull it out. So if I pull out one end, put it here so I can get a good contact, then I measure this. I've got 0.979. I could just call that, why don't I call that 980 ohms. 980. So I'll put that down here. So that's pretty close to 1K. So I've got 980 ohms right on that one there. I'll put that back. Then I'll kind of do these in pairs. So this one, .464, so I'll say 464 ohms. 464. And I think we were looking at 470 on that, so that's not too bad. Put that back over here. Do the same one on this, kind of just mirror images here. .463, that's not bad. I'll do that one. I think that's R3. That's the one I'm expecting about 100 ohms on. 99.6, that's pretty good. Again, with resistance, I don't have to concern myself with the polarity here. I can put the black and the red wherever it's convenient. 100.5. So that one's a little more than 100. The other one's a little less than 100, but still well within tolerance. So lastly, I need to measure these. So that's 2.158 K. So 2.16 K. .16. Okay, so let's see what we've got here. So I've got the resistors down, and I actually put them on the picture because it's labeled a little oddly. I mean, these are both R2, this is R1, and each one of these is R4. So I tried to just put the actual value here. The only other thing that I need to be careful of is I've got mixed units. These are all ohms up here. These are K ohms. So be very careful of that. Well, I think with that we're ready to get started. I'm going to take the voltage Vs there. I'm going to get that, and then I'm going to record the currents, this being the I1 and this being I3, and this one then being I2, like that. We've got the currents, and we've got our voltages. We'll reference this ground point there. I think we'll get this wrapped up pretty quick and easy. So before I power up, let me double check. I've got this resistor here. Then this point here where these three are coming together is this. This point here where those three are coming together is that. I've got these two coming together, and that's the positive right there. And I have these coming together, and that's the negative right there. This point here, that would be our point D, and this point here would be this point right over there that doesn't have a label. So I think I've got it put back together after taking the resistance. I think I'm ready to go. I'll go ahead and power back up. I'm going to change this to volts. So put this on volts with a straight line so that I get the, when I'm measuring the voltage. I'll go ahead and maybe I'll switch over and measure current. I'll do it in the order that it is. Let me check the source voltage. This Vs, I believe we were supposed to be 6 volts. So I can measure from there to there, and I should be 5.94, 5.95. That's close enough. 5.95. Okay, so I'll switch tools on you here, just because I've got this rigged up with slightly different leads. And also when we go to measure current, I switch the from over here, this is where I measure volts and ohms, and I move over here, I'm going to be measuring milliamps and microamps, because you did your calculations, so you should know roughly what the current is, so you know we're not going to be anywhere near 10 amps. So the other thing to mention is, and this probably go way out of focus, but we could use our old friend, the analog meter here, but we're going to be measuring one value that's really close to 0, so it's probably going to be nicer to have our digital meter. But if we were in a lab face-to-face, you'd probably be using these meters here. And the other thing is with my camera, the parallax is really bad. I noticed when I watched the video last time that I said, well, it's just under a value, and it didn't look like it was just under. It looked like it was significantly under. But when you see it in real life, it actually looked pretty good, and the camera gives it quite a bit of parallax. So maybe that's an advantage here with the digitals. You don't have parallax on the digital. So bring this over here to measure milliamps, and I will turn this off momentarily. And I'm going to pull this resistor out because I want to measure current 1. Okay, fire this thing back up, and it looks like 0, doesn't it? Okay, well that's milliamps, and if you ran the calculations on this thing, you'll know that your answer is pretty close to 0. Probably mathematically you didn't get exactly 0 because you've got round off as your calculator tries to do the matrix and whatnot. You may have something like point something times 10 to the minus 6 or something, but that's effectively pretty close to 0. Let's go a little lower on the scale. We can actually go to microamps here, see if we can get anything. It looks like pretty much 0. So I'm going to write down I1 as 0 milliamps. Okay, and this is a couple things with that. You always want to start out with a scale that's large enough that you're not going to hurt the meter. I knew that I was going to not be more than a few milliamps, so I started in the milliamp range. If I was going to be several thousand milliamps, then I'd want to be in the amp range. And then as you get a value like this that's very small, then you want to go to a smaller scale and see if you can pick something up. Okay. The other thing is when we used to do this lab, I guess last year, face-to-face, and many years before, I always have students, they'd be measuring this, and it was particularly problematic with the analog gauge, is the needle wouldn't move at all, and they'd say, it's not working, and I'd ask them, well, what did they calculate it as? And, well, about 0. I said, well, what is it measuring? It's measuring about 0. So I think if we've done our calculations right, I think this is confirming that. So turn my power off here. I can put this back together. So that was measuring my I1. Let's measure I2. So I will pull this one here off, put this here, and bring this around right there. And when we fire this thing up, so I've got 2.16, so 2.15, maybe I'll write that down. So that's I2, 2.15. And this negative is always a little hard to decipher. But what I'm going to do is I'm going to keep my color scheme the same as I move over to this other side. So I'll keep the black up on this, and I'll keep the red on the end of the resistor. And we'll see if that negative sign goes away, indicating that these currents are opposite. Because if you've done your calculation, you probably realize that these currents are the same magnitude, but they are opposite in direction. Okay, so turn this thing off. Okay, so again, I'll put the black lead there, the red lead here. Turn this thing on. Okay, so I've got the 2.16. So it looks like, according to these leads, that the current, this is measuring a negative, and over there it was measuring a negative. So let me put this back together and then talk about that. Now, I guess if I wanted to get rid of that negative sign, I could just switch these. Okay, so by switching those leads, you see that I got rid of the negative sign. Okay, well, let's see if we can get that accounted for. I think I've got that put back correctly. So if I look here, I've got this current that is going this way, and I've got this current that's going this way. So I measured these the same, so I would expect one to be different. I think if you go through your calculations, you end up with one with a positive sign and one with a negative sign, indicating that one is going the opposite direction. I don't want to spoil the surprise on the calculations, but one's going the opposite direction, which would mean they're either both going up or they're either both going down. And that's what I really measured. When I hooked these things up the same, I got a negative sign on both of them. If I'd have switched the leads on both of them, I would have got a positive sign on both of them. So they are not going in opposite directions like we see here in the diagram, which is fine. So if I look at my data so far, I have my VS, and then I've got I1, that's 0, and that really is 0 because I went clear down to microamps, 10 to the minus 6 amps. This is 2.15 and 2.16, and we could either say these are both negative, or I will say that I switched the leads. You saw me do that with I3 and get that as a positive. So the last thing I need to do is measure the voltage. So I'm going to go ahead and turn this thing back on. I've got this meter set up for DC volts. And let's go do that. I'm going to measure the voltage AC. AC. So I'm going to put the red lead on A. That's up here. And the black lead on C, and we see that we have not much. Okay, maybe I'll go down to millivolts. So I go down to the millivolt range and see what we can come up with. Should less than that. I might not have good contact here. There we go. So I'm reading in millivolts, and there is 0 millivolts. Okay, so I'll write that down, 0 millivolts. So I not only found a 0 in terms of volts, with 0 volts I actually measured lower and I have 0 millivolts. Well, let me turn back to volts and measure VA. So that's putting this one here at the ground and this one at the point A that's going to be up here. And that's, you can see across there, 4.92. 4.92. And that's volts. And if again I take this and go to there, 4.93, 4.93, 4.92, I'll say 4.93. So that's VC. Where was B? Well, B is this point here, so that's going to be, that should be pretty close to 6, 5.94. And finally D, I think D is just kind of practice right there. So put this here, that there, 4.71, 4.71. And finally I need to finish up with CD, so I will put the red at C and the black at D, so that's CD, 0.215. Volts. And DA, that would be the red at D, excuse me, yeah, D, with reference to A, so the black at A. So minus 0.214, minus 0.214. Okay, so I think that's our voltage measurements. Let's see how we did. So we've got, it's kind of interesting, I measured this voltage at D. This was, across here was 4.71, right? Whereas the voltage at C was across there, that's 4.93. So then the voltage at C with respect to D, we just got that at 0.215. Does that make sense? What if I take 4.71 and add to it 0.215? What do I get? I get pretty close to 4.93. So these are adding up pretty well. I like those. I think that will be good for our laboratory. So then, with our lab questions, write a matrix equation using mesh or loop analysis to solve for currents I1, I2, and I3. Use the measured resistance values. So we're going to come back here, use these measured resistance values, and you should then come very close to your calculations for I1, for I2, and for I3. Okay, so remember what I had you doing a little earlier. I had you doing this calculation, but this was just for the nominal values right there. We get some more practice doing it here for the actual values of resistance, and that should get you even closer to your measured value of current. Then you can explain why VAC is equal to VA minus VC. And hint, that was the Kirchhoff's voltage law that we talked about. We actually spent quite a bit of time before we started our measurements talking about that, so go back and look at that. And then comment on the relative magnitude of I1. That's the one that was very close to zero or was zero. Well, if our voltage, we said that our voltage across here, the voltage AC, was 0 volts. If the voltage across there is 0 volts, how much push is there pushing current through this resistor? Well, there's no voltage across here. There's no voltage across there. So using Ohm's law, if you solve for current, voltage over resistance, if your voltage goes to 0, your current's going to be the same. So that should be easy to deal with. And then finally, discuss any differences between your calculated and measured values. Okay, even when you take the resistance into account up here, you may have a few differences in terms of accuracy of the meters. Hopefully we didn't have any gross errors, but there's probably some error in the meters. Let's not blame too much again on resistance of the wires. I think you're actually going to be fairly close. So that'll be a good way to wrap up the lab. Well, I will get the data to you, and you can go ahead and get started doing this. Make sure that you really spend some time and get comfortable with doing mesh analysis and making sure that going through this process becomes second nature for you. So that's one of the big takeaways from this lab. How do you measure resistance without measuring equivalent resistance? How do you measure current, and how is that different than measuring voltage? Remember, we had to open the circuit. And then also, this lab is just really the make or break. Do you know how to do mesh analysis? Well, with that, I will leave you be and turn you loose. Talk to you next time. Thanks for watching.